You've sat by a campfire 1,000 times. When it's time to leave, you pour a bucket of water over the logs, and the flames vanish. It is just a fact of life. Like in Pokemon, water type simply beats fire type. Or maybe you were taught that the water just smothers the oxygen. That is the whole story, right? Wrong. The real reason water kills fire is a hidden, microscopic catastrophe. Discovering what actually happens in that vanishing flame reveals a breathtaking mechanism of energy that will completely change how you see the world. Think back to when you were a kid sitting in a science class. Your teacher probably drew a simple shape on the chalkboard, the classic fire triangle. 3 rigid sides holding the whole thing together: fuel, heat, and oxygen. You were taught that if you take away just one of those sides, the structure collapses and the fire dies. It makes perfect sense. So, when you ask almost anyone why pouring water on a log puts out the fire, the answer is always the same. They will tell you that the water covers the wood, creates a barrier, smothers the flames, and chokes off the oxygen supply. It sounds perfectly logical. It is easy to remember, but here is the problem. Let us actually look closely at what happens in the real world out in the open air. Imagine that campfire again. You throw a bucket of water onto the blazing wood. Instantly, yet you hear a loud hiss, and a massive cloud of steam billows up. Now, it is true that steam is a gas, and gases take up space. But to actually suffocate a fire, to completely starve those atoms of the oxygen they want, that steam would have to aggressively push away almost all the air around the logs. It would need to make up something like 90% of the atmosphere right above those flames. Think about the physical nature of steam. What does it actually do? It rises. It is hot. It is lighter than the surrounding air, and it immediately drifts up and away into the sky. It does not just sit there forming a tight, impenetrable bubble over your logs. Out in the open, the wind is blowing. Fresh air, packed with eager, restless oxygen atoms, is constantly rushing in from all sides. In an open space, or trying to block oxygen with a rising cloud of steam is completely useless. The oxygen is still right there, floating around, constantly bumping into the wood, millions of collisions every second. You might say, well, what about the liquid water? Does the liquid not coat the wood and create a physical wall? But think about the timeline of the catastrophe. By the time the liquid water actually manages to coat the surface of that scorching wood and stay there without instantly boiling away, the fire is already dead. The raging flames are already gone. The explosive reaction has already stopped. The liquid water did not kill the fire by simply blocking the oxygen. The fire was violently halted before the water could ever act as a damp blanket. So, we are left with a strange situation. The oxygen is still there. The wood is still there. And the fuel and the oxygen are right next to each other, physically touching. But suddenly, they cannot react. The terrible catastrophe stops. The snapping and the violent chain reaction simply cease. If the water is not suffocating the fire by pushing away the oxygen, then what exactly is it doing? What invisible force is water using to stop the atoms from doing what they desperately want to do? To understand what water is really doing, we have to look much closer. We have to shrink down and look at the atoms. In that piece of wood, you have carbon atoms. In the air around it, you have oxygen atoms. They actually desperately want to be together. If they get close enough, they snap together and release a massive amount of energy. But there is a catch. There is an invisible barrier keeping them apart. It is exactly like a ball trying to climb over a steep hill to fall into a deep volcano hole on the other side. If the ball is just rolling slowly, it goes partway up the hill, stops, and rolls right back down. Nothing happens. To get over that barrier, the ball needs to be moving very fast. In the world of atoms, speed is what we call heat. Heat is nothing more than atoms jiggling and wiggling around. Now, when you put a match to a piece of wood, you're making its atoms jiggle violently. When they jiggle fast enough, they slam into the oxygen. They climb over that invisible barrier, and they snap together. That snapping releases more heat, making the neighboring atoms jiggle even faster, causing a wonderful, terrible catastrophe of chain reactions. That jiggling catastrophe is what a fire actually is. So, how does water stop this runaway train? Let me give you a beautiful example you can try yourself. Imagine you take an ordinary, thin paper cup. You fill it with water. Now, you take a lighter or even a blowtorch and hold the open flame directly under the bottom of that paper cup. Your common sense tells you the paper should instantly catch fire, burn through, and spill water everywhere. But it does not. And the paper might get covered in black soot, but it absolutely refuses to catch fire. Why does it not burn? Because of that energy barrier. For paper or wood to catch fire, its atoms need to be heated to at least 150 degrees Celsius. That is the minimum jiggling speed required to climb the hill. But the water sitting inside the cup acts as a master energy thief. As the flame tries to heat up the paper, the water instantly absorbs that heat. It steals the jiggling motion. And liquid water has a strict, unbreakable rule. It will not get hotter than 100 degrees Celsius. By aggressively stealing the heat, the water locks the temperature of the paper cup right at 100 degrees. The atoms in the paper are trying to jiggle faster. They are desperately trying to get over the hill to meet the oxygen, but the water constantly pulls them back down. They never reach the necessary speed. The barrier remains unbroken. The fire starves, not from a lack of air, but from a complete lack of atomic motion. But this brings up a massive physical problem. The fire is pumping out incredible amounts of heat. If the water is stealing all of it, what exactly is the water doing with all that stolen jiggling? So where does all that stolen jiggling go? If the water is taking all this violent energy from the fire, why does it not just keep getting hotter and hotter? Because water has a secret. It uses all that stolen energy to perform a physical magic trick. It changes state. In liquid water, the molecules are essentially holding hands. They are sliding past each other, but they are stuck together in a group. To become steam, to fly freely away into the air as a gas, they have to completely let go of each other. And tearing those molecules apart takes an absolutely astonishing amount of energy. This actually answers one of the most fascinating questions people ask about this process. What if you took a bucket of boiling water that is already fiercely bubbling at 100 degrees Celsius, and threw it onto a fire, and it is already incredibly hot? Shouldn't that hot water just help the fire stay alive? Not at all. Reaching 100 degrees is the easy part. The real theft happens at the exact moment the water makes the final jump from a liquid to a gas. To break those molecular bonds and turn into steam, water demands a massive energy toll. It is one of the greediest substances in the universe when it comes to absorbing heat. When that liquid, even boiling hot liquid, hits a roaring piece of wood, it acts like a black hole for energy. It violently rips the heat out of the wood just to fuel its own escape into the air. The fire is working incredibly hard. The carbon and oxygen are trying to snap together, trying to release energy, trying to keep the catastrophe going. But the water just swallows every single bit of that energy whole. And when you dump water on a flame, you are presenting the fire with an energy problem that it simply has no means of solving. It is an atomic bankruptcy. The water steals the jiggling motion much faster than the fire can possibly create it. The atoms in the wood suddenly find themselves slowing down. They are completely robbed of the speed they need to climb over that invisible barrier we talked about. The carbon can no longer reach the oxygen. The snapping violently halts. The chain reaction collapses entirely. Water does not kill fire by suffocating it with a blanket. It kills fire by draining its momentum. It is the greatest energy thief in nature. But that brings us to something even more profoundly strange. Think about what water actually is. Why does it not just catch fire itself? If water is just hydrogen and oxygen is what fire desperately wants, why does water itself not burn? Why does tossing a bucket of water on a fire not just add more fuel to the catastrophe? Because water is already burnt. This sounds absurd, but think about what fire actually is. We said fire is the violent snapping together of atoms that want to be together, like carbon and oxygen. Well, hydrogen and oxygen also desperately want to be together. And when they finally get over their energy barrier and snap together, the resulting explosion is terrifying. It is literally rocket fuel. When hydrogen and oxygen burn, when they do that violent dance and lock together into their lowest energy state, the molecule they form is H2O, water. Water is not the opposite of fire. Water is the ash of a fire that has already happened, and it is the leftovers of a microscopic explosion. Those atoms have already snapped together. They have already released all their energy. They are completely exhausted. They are sitting in the deepest, most stable volcano hole possible, and there is absolutely nothing left for them to give. But wait, if water is just dead, exhausted ash, how does life exist? The entire planet is covered in this burnt-out liquid. Your body is mostly made of it. Trees, grass, and every living thing depend on this dead, zero-energy molecule. How do you get living, growing forests out of chemical ash? Here is the grand twist. You have to run the fire backward. To unburn water, to tear those exhausted hydrogen and oxygen atoms apart so they can be useful again, you need to put all that massive explosive energy back in. But where on earth could a tiny green leaf find the staggering amount of power needed to rip apart a water molecule? It does not find it on Earth. It looks up. It uses the sun. A plant reaches its roots down and drinks up the dead burnt ash we call water. Then, it spreads its leaves and catches the intense, jiggling light rays fired directly from the sun. The plant uses that solar energy to physically grab the water molecule and violently rip the hydrogen away from the oxygen. It takes the hydrogen, combines it with carbon from the air, and builds its own body, the wood, the leaves, and the branches. It then spits the oxygen back out into the air as waste. So when you look at a massive oak tree, you're not looking at something that grew out of the dirt. You're looking at a magnificent structure built out of air and water, is stitched together by the sheer, raw power of sunlight. And that changes exactly what we are looking at when we see a campfire. So let us bring this all the way back to where we started. You are sitting by that campfire in the woods. You are looking at a burning log. But now, you know you are not just looking at wood disappearing. You are watching a spectacular cosmic reversal. For decades, that tree stood in the forest, acting like a giant, living solar battery. Every single day, it reached up into the sky and captured the blinding, violent energy of the sun. It used that raw solar power to painstakingly rip apart exhausted water molecules, forcing the hydrogen to lock together with the carbon from the air. It stored all that sunlight deep inside its wooden rings. It locked the energy away, holding those atoms in a state of incredible tension, just waiting. And then, you came along. You struck a single match. You gave those atoms just enough heat, just enough of that jiggling motion to climb over the edge of the invisible barrier. And the moment they did, the trap sprang open. The carbon and hydrogen violently snapped back together with the eager oxygen in the air. And as they locked back into their dead, stable state, as they turned back into invisible carbon dioxide and water vapor, they released everything they had been holding on to. The bright, dancing flames you see leaping off the log, that is not just fire. That is the actual sunlight that fell on those leaves 50 or 100 years ago, finally being let out. The heat that warms your hands on a cold night is the exact same heat that traveled millions of miles through the freezing vacuum of space to hit this planet decades before you were even born. You're literally warming yourself with trapped, ancient sunshine. And a campfire is just a tree running its life backward, returning its borrowed energy to the universe. Water kills the fire because it steals that momentum. It demands a massive energy toll to turn into steam, stopping the atoms from dancing and turning the violent release of sunlight back into a quiet, cold, exhausted process. But if every piece of wood on Earth is just a temporary battery storing the sun's power, and every fire is just the release of that borrowed heat, it leaves us with one final, undeniable question. If the sun is the ultimate source of all this jiggling, all this energy, all this snapping and building and burning, where exactly does the sun get its fire? How is it that a giant ball of gas in the middle of absolute nothingness is so unbelievably hot, so relentlessly jiggly, that it can power the existence of every tree, and every fire and every breath on this entire planet? That is a different story. I will leave you something to imagine.